Perfect. I'm going to follow up on this. I'm working as well with Jacob, Prial, and Thomas, and we're working on using heavy minerals as proxies for igneous processes. So what I'm going to do is more or less build on what was previously done and why this is important, and just show you some results of what we've been doing elsewhere in Canada to show how zircons are really useful for trying to understand magmatic processes and VMS systems, but also give us some idea of metal endowment and physical chemical conditions of magmatism. And then I'll end more or less by why we think the Superior is a great place to test some of these ideas, and then just sort of a workflow of how we see things going in the future. Many of you folks have seen this stuff before. VMS deposits are related to magmatism. They occur in specific tectonostratigraphic environments. There's a definite thermal relationship between VMS deposits and magmas, and there's probably a genetic relationship as well. And a lot of the work that's gone on and looking at the petrology of felsic volcanism associated with VMS has really been focusing on trying to understand the tectonic settings and so on and so forth, and discriminating prospective versus less prospective environments. There's been delving into understanding the petrology at various scales. For example, the depth of melting using the classifications of Lesher and others. You can integrate it with felsic and mafic rocks to try and understand tectonostratigraphic environments. But I think there's a real knowledge gap that's missing, and Jacob alluded to this with respect to sort of metal endowments and how do these magmas form, things like temperatures and placement, physical chemical conditions like FO2 and so on, and then the bulk contents of metals that are present. And so one of the beauties is the melt inclusion world, as well as a lot of lessons that have come from the petrology world in the last decade due to advancements in microbeam technology, as well as our colleagues in the porphyry and epithermal world. We can use things like zircon, monazite, apatite, and their associated melt and mineral inclusions to tell us something about the magma processes and then potentially VMS genesis. And so I'm just going to show you a few things from my own group's work in Western Canada. We've been doing a lot of work on trying to understand VMS hosting felsic magmatism, and then coeval, age, and basement that melted the same basement but different barren assemblages. And some of the things we're seeing are quite interesting. We're seeing these extremely interesting inclusion assemblages found in things like zircons. You don't need to worry about the details here, but this is all from the Finlayson Lake district in Yukon. These deposits are predominantly zinc rich, but they also have copper and other things. And we see a wide range of things like zinc alloys, copper, lead sulfides. You see glass is preserved. We even see things like platinoids, as well as things like chlorides and so on. So when you compare this to barren assemblages in Yukon, you don't see that. And so some of these zircons are recording that the magmas themselves were metal enriched, meaning that they could have either degassed metal into the hydrothermal systems, or the rocks themselves are metal rich such that you could leach those metals out during leaching episodes in hydrothermal activity. The other thing we've been doing is looking at mineral chemistry and in situ hafnium isotopes of zircons. And there's a lot of material here. The only thing that really matters is one of the things that we've been documenting in zircons in the Finlayson Lake district is this association of there's a crustal influence. This is hafnium isotopes. Negative values in zircons generally reflect increasing amounts of crustal material. The more positive they are, the more mantle material you see. The higher the thorium-uranium ratio in zircon, the more and more juvenile or mafic component you see in the zircon. And one of the things we see associated with VMS versus barren assemblages is this shift towards more juvenile signatures, as well as higher thorium-uranium ratios, which we're interpreting to reflect the upwelling of basaltic magma beneath the rifts. That's driving the magmatic process, but potentially maybe driving hydrothermal systems as well, adding extra heat to the base of the crust, as well as potentially metals. And we're also using other things like titanium and zircon geothermometry, as well as looking at the rare earth element chemistry, for example, the cerium anomalies and europium anomalies, to give us ideas about the FO2 and zircon temperatures of emplacement. And the details here are not critical, but these are generally the VMS bearing, these are the VMS bearing zircons. These are ones that are associated with coeval arc rocks that are barren. And generally we see, as would be expected in arcs, we see more oxidized conditions, whereas in the back arcs, they're more reducing. Even within the same camps, however, this is relative to the phalite quartz magnetite buffer. You can see here iron woostite. These are the VMS related ones. These are the ones that are in the arcs. Even within the camps, however, we can actually identify some specific units that are hundreds of meters in thickness that have specific zircon chemistry that are distinctive from those elsewhere in the district that don't host mineralization. So some of this stuff is turning out to be quite interesting. This is work that's been done by one of my PhD students, Matt Manor. So why is the Abitibi a great place to test some of this kind of stuff, and the Superior in general? It has wide ranges of metal contents and endowments. And I think if you look around things like the Matagami camp where you have zinc enrichment, you've seen work that's come out of the Doyambusque-Laurent. You have things like Noranda, that's polymetallic kid, and then you also have assemblages that have lower tonnages and minor mineralization, things like the equivalent Blake River group rocks in Clifford and Ben Nevis Township, things like the Swayze Greenstone and Kamkosha. These look like, the way I would think this could move forward is actually using these things to actually test the idea, do we see unique assemblages that are proportional to the metals that are present in the VMS deposits? Are there specific physical-chemical conditions that are associated with variety of deposit types and metal endowment, and so on? And do we see differences in crustal basement depending on the metal enrichments? And this sort of dovetails a lot with what David Mole and others are doing. In the short term, we're just waiting. We had a postdoc advertised in fall 2020 and had lots of applicants, of which a number were outstanding. The goal is to work with existing metal earth researchers to dovetail with their broader crustal architectural work. I think where we fit in is mostly trying to get into the igneous processes at the deposit scale. Our general workflow is we have zircon suites that we are obtaining from people, from archives and so on. The initial work is being done by Jacob and Priel. We're then mounting these, getting them imaged at Colorado School of Mines, and then they're getting sent to me, and I'm going to use those CL images and so on as the means to do SEM probe and laser ablation split stream work. And hopefully we can work into other phases like monazites and apatites later on. So that's pretty much where I come from. Right, thank you.
Thanks, Dean.
Oh, sorry, I got to
Stop sharing the screen.
Yeah, perfect. Thank you.
You're up, David.
Thanks, Harold. I hope everybody can see the screen all right.
Yep, looks good.
Perfect. My name is Dave Diekrup. I'm a postdoc with Mark Hennington at the University of Ottawa, where we're working on the VMS trace element subproject 3B. I'll get right into this quick 5-minute proof of concept and overview of the project. The primary question we have in this project is what we can learn about regional fertility and metallogeny from trace element fingerprinting VMS ore. And this question ties directly into the Craton and Transect work that we heard about earlier in the week. And I'll give some context about that connection shortly. There are two underlying concepts that needed to be tested. The first one is that enrichments and depletions are actually consistent among deposits in a district and not just locally controlled. So what we're seeing is a regional signal, and there are no local processes that dominate the trace element contents. And the second concept is then to identify what signatures are indicative of conditions favorable for base metal deposition. We started out combining legacy data and archived samples based on a recent GSC open file, and we now about doubled the size of that initial database to include a representative number of VMS deposits in Canada. But the focus of our work is on the Abitibi, and more than half of the analyses that we have in the database right now are from Abitibi VMS, although there are still gaps in our coverage. So the red ones are the deposits we have, the yellow ones are existing deposits that are not included in the database yet. So the northern Abitibi is underrepresented, but we're working with Metal Earth collaborators to obtain samples hopefully very soon, including some field work again, to achieve some better coverage. For the general metal contents of VMS, we have known for a while now that there are large-scale crustal and temporal variations that are represented in the copper, lead, zinc contents of VMS systems. And the majority of Archean VMS deposits plot on the copper zinc line, with virtually no lead compared to Phanerozoic deposits. However, there are a number of Archean districts that are notably enriched in lead and silver, for example, including nearly all of the deposits in the Slave Craton, the Sturgeon Lake, Greenstone Belt, Chotel, Val-d'Or, Manitowoc, Kid Creek. They're all plotting well off the copper zinc line here. This strongly hints at crustal differences, such as early arc-like assemblages or keratinization compared to more primitive greenstone assemblages. And the differences are matched by the lead isotope data that we've seen earlier in the week during the Craton and Transect scale projects. The archive samples that we're working with include both underground and drill core samples representative of different ore types, as well as different daily and monthly concentrates from the mill. And we were naturally concerned about how representative these graph samples might be and if they would introduce a bias into our data set. So this plot here shows the arsenic contents of chalcopyrite mineral separates from ore samples of different deposits compared to arsenic and copper concentrates from the same deposit. And the latter representing a much larger bulk sample that may have been made months or years apart from the grab samples. And this shows that the grab samples are generally matching the monthly copper concentrates over a wide range of tens to hundreds of ppm of arsenic in different deposits. They are somewhat higher in the ore samples than in the concentrates, but there is clearly differences from one deposit to the next. And this gave us some confidence that the trace element signatures of even individual samples can provide us a good first order fingerprint from one deposit to the next, much like lead isotopes or sulfur isotopes do. That process and that observation is reflected on a CAM scale where we can see clear differences. For example, here the arsenic contents of sulfides from Noranda are consistently averaging around 100 ppm with many samples at much lower concentrations. But as soon as we step out of the Noranda main camp, arsenic concentrations in sulfides increase dramatically, first in the cycle 4 deposits like Delbridge and Mobran, and then throughout deposits like Busquet and Val-d'Or, with average concentrations much closer to 1,000 ppm. This in part, but obviously not entirely, reflects host rock differences and suggests some more fundamental crustal differences that we will be testing with other elements. We have similar data for about a half dozen other districts in the Superior province that show a large range of arsenic and sulfides spanning several orders of magnitude and generally increasing from Noranda through Matagami, Chotel, Kid Monroe, Busquet, Val-d'Or to Sturgeon Lake. Even if we're taking into consideration differences in local host rocks where there are, for example, more felsic at Busquet and Sturgeon Lake, it still seems likely that there is a trend here that at least partly reflects progressive keratinization from more to less primitive, with a big jump to Proterozoic deposits and then Paleozoic and younger deposits. And this is just for one element. We already saw similar trends in the lead data, and we're now exploring another 30 to 40 elements in the data set, including with multivariate statistics and machine learning approaches. And we think that this is going to tell us something about the crustal influence and possibly the fertility in different districts, especially when we relate the trace elements in VMS deposits to the findings from the Transect and Craton scale projects. So we're trying to provide another layer of information to what the other groups are doing. I will leave it at that. Thank you. My apologies if I went over time. Back to you, Harold.
Thanks, David. Thanks, everyone. Questions? Any questions? There was some in the chat box, but I think they've been answered. Any questions?
I've got one stuck in the chat box, but I think it may point to some kind of a fundamental bias in the work that Jacob and his student are doing, because what he seems to show is a very high proportion of alkaline rocks, and that's not a prominent feature of Archean volcanism.
Okay. Was that Jacob or Piercey?
It was in the melt inclusions.
Oh,
I
okay.
could comment. I could comment. I'm not sure if the bias is kind of targeted at the community or me, but you know, the issue is that what we're seeing at surface is the end product of contamination and the end product of a lot of things. And so, you know, our zircons, in the case of the Doyon Bousquet Laurent camp, are reflecting compositions that are trapped at source. And there, in an example there where we know that the field relationships, petrography, and some geochemistry hints at a TTG type complex, the melt chemistry is very much falling into the alkaline field at depth, very oxidized alkaline liquids, at least at the stages that the zircons and quartz are trapping melt inclusions. And so I think the important point I'm trying to make here is we need to go at this with an open mind in terms of what our bulk rock geochemistry is showing us. If you plot the Bousquet volcanics on plots to show their affinity in terms of various possible reservoir compositions, they're overwhelmingly contaminated, and a lot of the alkaline signature has been destroyed through that process. And so I think the zircons are going to give us a snapshot of what is happening at depth in the mid to lower crust at the stage of magmatic evolution before emplacement and before much of that upper crustal contamination.
Interesting.
Jake, it's Mike Hamilton.
Hi there.
I was curious how much compositional spread you're seeing in your melt inclusions in zircons from a given sample. Is it pretty restricted, or are they actually recording quite a range?
There is quite a range when you look at the population of zircons coming from an individual lithology. Within individual zircons, the problem is you tend to only get like one or two inclusions. So the zircons are sampling melts at different stages, but there seems to be you know, a fairly wide range of compositions reflected, and they fall on fractionation trends, and you can identify, you know, depending on whether the inclusions are coming from the cores of zircons or the rims, you may be able to connect that to you know, the entrapment of earlier liquid phases versus later liquid phases. And so there is a, you know, very clearly a protracted history, obviously, that we recognize in zircon geochronology, but it's reflected in the melt chemistry, and that range can be quite wide.
Yeah, it'd be very interesting to see that data in detail. Yeah, thanks.
Are there any further questions, comments? There is, folks, there is a fair number of comments and questions in the chat room. Maybe you can address that. If there is no more questions from the audience, we're due for a break, and we'll take an hour break, and we'll reconvene here at 1:30, and we have several interesting talks to finish off our day.